Hi, I'm Norman Walberger. Today we're going to introduce projective geometry into our study of hyperbolic geometry. I claim that hyperbolic geometry, when you do it in the right way, is essentially projective geometry plus the study of one individual conic, which we are going to take as a circle to be the simplest. So it's going to be important for us to learn a little bit about projective geometry, which is a very important classical subject. It used to be a mainstay of the education of any mathematics student. But these days it's sadly neglected, and it has dropped out of high school curriculum and many university curriculums too. It's a very unfortunate situation, and I hope that perhaps the realization that it actually underpins hyperbolic geometry will lead to a resurgence of interest in this beautiful and important subject. So if you're an undergraduate mathematics major and you haven't studied projective geometry, this is a chance for you to catch up on something that's really important. So the subject arguably starts with Pappus. We've already talked about him. We've talked about Pappus's theorem, which is a theorem only involving the straight edge, which is roughly what projective geometry is. But it really kicks off with the work of Gérard Desargues, a French engineer and mathematician in the 17th century, who worked almost by himself, developed the basic understanding of this new subject. One of the very few of his contemporaries that appreciated what Desargues was doing was the young French genius Pascal, who made an important contribution to this subject as well. The subject then languished for almost 200 years, until in the 1800s it was taken up by a whole slew of people. Poncelet, Mobius, Plucker, Chasselet, von Stout, Klein, many others ended up contributing to this resurgence of projective geometry. And one of the key new innovations that the 19th century mathematicians introduced was a new understanding of what projective geometry actually was. To Desargues, projective geometry was what you get when you take the usual Euclidean plane and you add some points at infinity. Just the points that you need so that parallel lines now somehow magically meet. This is a little bit mysterious and a little bit ambiguous. But in the 19th century, people realized how to think about this in a way that removed all the ambiguity, that made it as plain as day what the actual projective plane was, and connected it very intimately with linear algebra. That's the point of view I'm going to adopt today. I'm going to tell you how the 19th century people understood projective geometry in a very simple and natural way. And this is going to lead us to a revision of a very fundamental understanding in geometry. Historically, there's been a big divide in the subject between so-called Euclidean geometry and so-called non-Euclidean geometry. And this is reinforced by most of the texts in the subject, and most professional mathematicians these days will think in terms of the subject being divided into these two different halves. It turns out this is not the right way of thinking, and it's ultimately a barrier to understanding geometry properly. So if you've been trained to think this way, I'm going to ask you to let that idea go. Let it go. Forget about this division between Euclidean geometry and non-Euclidean geometry. It's not the right way of thinking. The more modern, more insightful, the more important understanding is this one here. Here is the real major division in geometry. It's between affine geometry and projective geometry. These are the two sides of the coin that together combine to form geometry. And they're linked. So there's a very close connection between affine geometry and projective geometry, and arrows going in both directions. Now, some people will claim that geometry is really more like this, and others will claim that it's really more like this. But I think it's best to have a balanced understanding, to appreciate that there are these two sides, and both sides are ultimately equally important. There are reasons and situations where this is more fundamental. There are other reasons and other situations where this view is more fundamental. But overall, we should think about this pairing, this balance between these complementary points of view. Now, on this half is where Euclidean geometry sits, but also variants of Euclidean geometry like chromogeometry that I introduced in my rational trig series. In fact, rational trigonometry, the way I've expressed it in my rational trig series, really fits in this half over here. But so does the geometry of Einstein and Minkowski. These are really affine geometries. Their natural home is an affine space, or closely connected, a linear or vector space. Over here in projective geometry, which is more what algebraic geometers study these days, this is actually the natural home for hyperbolic geometry and also elliptic geometry, as I'm going to show you. So I really want you to understand this division, that there's a division. Euclidean geometry is on this side and hyperbolic geometry is on the projective side. So the approach that we've taken to hyperbolic geometry so far in terms of Cartesian coordinates has been to adopt this point of view. We need to replace that with a projective point of view because this is the natural home for hyperbolic geometry. Now, projective geometry is much less familiar than Cartesian geometry, so I'm going to have to explain some basics about projective geometry to you, and that's what we're going to start to do in this lecture here. If you want some more information about projective geometry, some more motivation, some more history, I recommend Wild Trig, the series from 31 to 41. It's all about different aspects of projective geometry, and also the Math History 8, a little historical discussion of projective geometry. So, today we're going to talk about projective geometry, very basic fundamental things, the way that the 19th century people thought about the subject, and ultimately we're going to connect it to the circle. We're going to see the circle in a new light, which turns out to be an old light, going back to the ancient Greeks. The pioneering work of Gerard Desargues in the 17th century was motivated by questions that the Renaissance artists had struggled with, of how to represent a three-dimensional scene correctly, with correct perspective, in a two-dimensional representation of it, typically a painting. And these days we can see that there are two different ways of representing a three-dimensional situation in a two-dimensional plane. And roughly they correspond to the affine and the projective geometry points of view. So in the affine projection, what we do is we take our object, which we'll assume for now is that cube right there. We'll think of that as a real-life three-dimensional cube. And here's the plane of the easel, perhaps you can think of it, or you can think of it as a plate of a camera. And we want to represent the three-dimensional object on this two-dimensional plane. And the way we do it is by choosing a direction in space and drawing lines in that direction from the points in the object to where those lines meet the plane. And we always choose parallel lines so that the three-dimensional object gets represented by this two-dimensional image of its parallel projection. Now, this kind of projection, which you could call an affine or a parallel projection, has some very nice properties. One of the most important is that it maintains linear spacing. So if you have points which are equally spaced along some line in the three-dimensional object, then the affine projection of it will maintain that equal spacing. So here's a picture of what a cube would look like under such a parallel projection. The equal spaced points stay equally spaced. Another property is that lines which are parallel over here get represented by parallel lines over here. And this is very convenient for us when we represent three-dimensional space with an x, y, z axes. We're always using an affine or a parallel projection because that ensures that the spacing along all of the coordinate axes are actually equal in our image space. Now there's another kind of projection which is less used when we do elementary mathematics, but still quite important for practical applications. That's a projective projection, where we think of having an eye, a fixed point in space, which is looking at our three-dimensional object. And lines emanating from this eye to various points on the three-dimensional object will meet our viewing plane, this one right here, in, well, some new points which form the two-dimensional representation of this three-dimensional object. So the difference here is that all the lines are emanating from one single point, while over here they were all parallel. That makes a big difference in terms of the way the projection looks and the properties that it has. In particular, lines which were parallel over here are not necessarily parallel over here. So for example, these lines here, these ones, these ones, these ones, these ones, which are all parallel in the cube, will, under a representation, will all meet at a certain point on the horizon. So if this picture was done correctly, then this line here, and this line here, and this line here, which are all representing lines which were originally parallel in the three-dimensional picture, those lines in the picture should all meet at some point over there somewhere. Similarly, these lines should meet somewhere up there at some particular point. And another property is that the linear spacing along any line in the original here is not maintained in the picture. This distorts linear spacing. So for example, we get something like this, and as we move away, the spacing decreases in the image. Over here, the spacing was maintained. So this is sort of the realm of affine geometry, and projective geometry is interested in this kind of situation where we're actually viewing something as if from our eye. One eye closed, we're looking at the world, looking at a three-dimensional situation, taking a two-dimensional picture of it, and asking, what do these two-dimensional pictures really look like? So here's an important example of the difference between an affine view of something and a projective view. Let's look at a mathematical object, in this case the curve y equals x squared, which you all recognize as being a parabola, and here's sort of the standard picture of the parabola with x-axis, y-axis, equally spaced points along both axes. And I've drawn a kind of grid of lines that really completely tell us where everything is. Okay, so this parabola in red there goes through the point 0, 0, 1, 1, 2, 4, 3, 9, and so on. It looks like this. It goes up there. This is a very familiar picture of the parabola. That's an affine view because, well, we're representing it in an affine way. Parallel lines are still represented by parallel lines. Now suppose you were on a very flat surface and this was the ground and the parabola was stretched out in front of you on a flat surface, and there were no other trees or houses or anything else to obscure your vision. All what you could see was this infinite grid of lines with this parabola marked out. What would you actually see? Well, as you looked towards the horizon, you would actually see a line which was the horizon. What you would actually see would be something much more like this. This is actually a more realistic picture of a parabola viewed the way we would actually look at it. So we would be sitting over here somewhere. There's the x-axis as before, there's the y-axis, and there's the horizon. And we would observe that the lines which appear to be parallel over here the line x equals 1, x equals 2, x equals 3, and so on, those parallel lines, like railroad tracks, would all meet at one point on the horizon. The same point where the y-axis meets the horizon. And the other equally spaced lines become not equally spaced. As we move towards the horizon, they become closer and closer together. And this pattern is established by auxiliary construction, which I've explained in a number of other places, where you look at the diagonals. The diagonals in this picture are also rather important because all those diagonals, representing parallel lines, also meet at distinguished points on the horizon. And by use of these diagonal lines, we can actually construct this picture in an accurate way. And that was a major breakthrough for Renaissance artists interested in drawing tiled floors, for example, in a realistic way. Now, when we look at the parabola y equals x squared in this picture, we see something rather remarkable. There's the point 0, 0, point 1, 1, point 2, 4, 2, 4, point 3, 9 would be up here somewhere, 4, 16 would be up there. We join all those dots, we would actually get an ellipse. So what we would actually see in front of us on this infinite plane would be an ellipse. The parabola visually is an ellipse. Difference between an affine view and a projective view. So it was obvious to Desargues that there was something happening here that was not captured in this usual picture. And one of the important new things was this line at infinity. This was a new line that was actually part of the picture, but technically speaking, these points were not actually exactly in the plane. They were kind of at infinity. They were in some limiting position. So projective geometry wants to try to understand how do we incorporate this line at infinity and the points at infinity on it in a consistent way together with all the other points. Well, that's what the 19th century mathematicians figured out. They figured out how to have a unifying understanding which includes the points at infinity, like a horizon, in a way that's consistent with all the other points and other lines. It turns out that to understand projective geometry, it's best to start with a one-dimensional situation, which is already quite interesting and rich. So let's start with one-dimensional geometry rather generally. There are two major types of one-dimensional geometry. There's affine geometry and projective geometry. The affine geometry is simpler and more familiar, so let's start there. Here's the affine line. Okay, it's a line, and on this line we have a notion of equally spaced points. We have a notion also of translation. So we have this idea that the separation between those 2 points is the same as separation between those 2 points, same as the separation between those 2 points. Or the separation between this point and this one is the same as this one and this one. And we're allowed to compare relative displacements. So this vector u from here to here, we can say, well, that's -3 times the vector w. That's sort of what the geometrical content in our minds is for an affine line. The algebraic setup is very simple. Algebraically, we say that an affine point is just a number, x, enclosed in square brackets. And by a number, I always mean, unless I otherwise say, a rational number. And I'll use this notation for a rational number. I don't like the set notation. We'll just say that x is of rational type. So that's what an affine point is. It's just a very simple thing. It's just a number enclosed in square brackets. The square brackets is alerting us to the fact that we're talking about an affine point. Now, it's important to realize that this line here has no distinguished coordinate framework. It means that different observers can come along and interpret this affine point coordinate system in different ways. So here are two possible ways of interpreting or putting coordinates on the affine line. Mr. Blue says this, we'll call this point 0, we'll call this 1, 2, 3, 4, 5, and so on. This one, minus 2. And we can also look at intermediate values. That might be a half or a third and so on. Okay, that's Mr. Blue's coordinate system. While Miss Black's coordinate system says, she says, okay, we'll start with 0 there, and then 1 will be there, and 2 will be there, and 3 will be there, and -1, -2 in this direction. So both of those are consistent affine coordinate systems, ways of interpreting what an affine point looks like on the line. So for example, that point there, A, would in Mr. Blue's framework be represented by the point bracket 4, while B would be bracket 7. The vector from A to B, which we might call V, well, that's a displacement of 3 in the positive direction, and we can write this vector as a round bracket with a 3 inside, telling us that we're talking about a vector or a displacement between 2 points, not actually a point itself. While this vector over here, that would be the vector 1, round brackets 1. And Mr. Blue would be able to say this vector here is actually 3 times this vector here. Miss Black, on the other hand, would have different coordinates for these various things. In her system, this point here is halfway between 0 and 1, so that would be the point 1/2, while this point B would be the point 2. And she would describe this relative displacement, this vector AB, in terms of a vector 3/2, because it's a displacement of 3 halves. And this vector here would be a displacement of a half, or the vector 1/2. So even though her notation would be different from Mr. Blue's notation, she would agree with Mr. Blue that this vector here was 3 times that vector there. So they would agree on this. That's an affine line. In affine geometry, the role of vectors and points are subtly different, although they're very close to each other. Strictly speaking, a vector is determined by a pair of points. So if we have 2 points A and B, then the vector determined by them, AB, is something in round brackets, and what we put in the round brackets is the difference between the coordinate of B and the coordinate of A. Now we can have 2 other points, say C and D, and their coordinates will be x of D and x of C, so the vector CD will be the round bracket with x of D minus x of C inside it. And we would say that these 2 vectors are the same precisely when this number is the same as this number. So the 2 points A and B and the 2 points C and D don't have to be actually the same, but they have to have the property that their separations are the same. So from the affine space of points, we get a notion of vectors, which are displacements between points, or pairs of points, subject to this kind of equality. So we get this a little bit subtle association or distinction between the original affine space and an associated vector space, which is also one-dimensional, which we might call V. So A for affine space, the original space, V for the associated vector space. And the vector space consists of the vectors coming from this affine space. So for example, this vector U over here, going from here to here, that vector, can be represented in the vector space by this point here. The vector space is distinguished by having a designated 0. All right, that 0 represents the 0 displacement. And all the other points correspond to vectors in here. So this point here corresponds to this vector in the affine space, or equally this vector. While this point here corresponds to the vector V, this one here, or any other one which is 3 over. Now, here's Mr. Blue and Miss Black again. They have different coordinate systems in the affine space. And they would also have different coordinates in the vector space, but they would agree that this point represents the 0 vector. They would now agree where their origins are. So Mr. Blue would say this point represents the vector 1, while Miss Black would say this point represents the vector half. And Mr. Blue would say this point represents the vector 3, and Miss Black would say no, it represents the vector 3/2. But they would be agreed that you could add this vector and this vector to get u plus v. In coordinates 1 plus 3 equals 4, or a half plus 3/2 is 2. So the vector space has some structure that the affine space does not have. And that structure is some algebraic operations that you can do with the vectors. You can add them, and you can scalar multiply any of them. You can multiply any one vector by a factor of 2 or a factor of -1/2 or any other number. So that was one-dimensional affine geometry. What about one-dimensional projective geometry? Well, Desargues would have said, well, to get one-dimensional projective geometry, or the projective line, you take the affine line and you add one point at infinity. But the 19th century people realized that there was a better way of saying what one-dimensional projective geometry was. And they realized that to define one-dimensional projective geometry, we really need a two-dimensional vector space, which we might call V2. So a vector in this two-dimensional space is algebraically a pair of numbers now, in round brackets to alert us that we're talking about vectors. So this is the two-dimensional analog of the one-dimensional vector space, and it's a familiar kind of thing. There's x-axis, there's a y-axis. They don't have to be perpendicular. The x-axis has some equal scaling. The y-axis has some equal scaling, but they don't have to be the same kind of equal scaling. Separation here could look different from the separation here. But we're still then able to associate to a point in this space a vector. So this point here would be the vector 2, 1 in this coordinate system. This vector or point here would be the vector -3, -1. Now, vectors, just as in the one-dimensional situation, can be added like this, just component-wise, and they can be scalar multiplied, just like this. So scalar multiplying it just means that you're taking this vector, which we can sort of imagine as this segment here, and scaling it up by a factor of 3 to give us the point 6, 3. If we add this vector to this vector, well, we're doing it sort of component-wise, or geometrically. You're just going here and then going here, I guess here, and you'd end up with this vector -1, 0. Okay, so that's the framework that we need. Where does the one-dimensional projective geometry come from? Where is it visible? The key is to observe lines through the origin. Lines through the origin have some special property. Namely, say that line there, it's closed under both of these operations. So if you take any two vectors which lie on this line and you add them, then you stay on that line. And if you take any vector in that line and you multiply it by any scalar, positive or negative, you stay on that line. And it's got to be a line through the origin to have that property. If you look at a line not through the origin, it wouldn't have that property, because if you add this vector to this vector, you'd get something outside. But these lines to the origin have some special property. They're called one-dimensional subspaces. That just means that they're closed under addition and scalar multiplication of vectors. How do we specify such a line? Well, we could take any vector on it, say that vector right there, let's call it x, y in round brackets. And the line is more or less determined by that vector, except for the fact that we can multiply that vector by any scalar and we still have the same line. So we introduce the idea of a proportion. It's really the proportion between the two coordinates x and y which specifies the line. And this is our notation for proportion, this colon here. And we're going to agree, it's the usual notation, that we're going to put this proportion in square brackets. That's going to represent that line. And that's going to be what we end up calling a projective point. So the projective line is going to be what we get when we look at all possible projective points. I mean, all possible one-dimensional subspaces of this two-dimensional vector space. That is the one-dimensional projective line. All right, so let's have a look at these projective points forming this one-dimensional projective space. In blue here is our underlying two-dimensional vector space with an x-axis along there and a y-axis along there. And you see that the scaling is quite different on the two axes. 1, 2, 3 in this direction, 1, 2, 3 in this direction. And we're saying that we're now interested in all the lines, well, one-dimensional subspaces that go through this origin here, go through 0, 0. So how could we describe all these lines? Well, we've got these coordinates. So we, for example, this line here goes through the point 2, 1. It also goes to the point 4, 2, or the point 1, half. Or if we multiply by minus 1, we get down here, minus 2, minus 1. These are all points on this line. The line itself is going to be represented by the proportion 2 to 1. And I've chosen this point. We could just as well have chosen this point. We could have said it's the proportion 4 to 2. Because the proportion 4 to 2 is the same as the proportion 2 to 1. They mean the same thing. However, it's very convenient to choose the proportions so that that last or the second coefficient is 1. Because then it's kind of more canonical. Then we don't have to fuss about different possibilities. We pretty well only have one possibility if we insist that that last entry be 1. And what that really means geometrically is that we're intersecting these various one-dimensional subspaces with this green line, the line where y equals 1. So all the points along this line have y coordinate equals 1. So if we take one of our lines and just look where it meets the line y equals 1, that will be the point 5, 1, and that's then the name, the canonical name for our line. So 5, 1, it's a homogeneous coordinate for this line. There's 5, 1, there's 2, 1, there's the line 1, 1, there's the line 0, 1, there's the line minus 1, 1, line minus 2, 1, the line minus 3, 1. The line 1,000,000, 1 would be very close to horizontal because 1,000,000 in that direction would be a long ways away. In fact, there's one line that we haven't included in this labeling, and that's this line right here, which is also a line through the origin. It's rather special with respect to this green line because it's parallel to it and doesn't in fact meet it. So this line is not covered by this labeling. There's no point on the green line which is covered or meets this particular one-dimensional subspace. This is a little bit special. It's the case when the y-coordinate is 0. So any point along here has the form x, 0, and if we divide by x, we get 1, 0. So the name for this line is projective point 1, 0. By the way, we don't have to worry about this point here. 0, 0 is not an allowed proportion. We are not going to consider that. It's not a one-dimensional subspace because if you multiply that by any scalar, you still stay at 0, 0. So we're always choosing a non-zero point on a line to represent it in these coordinates. Okay, so there's really two different kinds of situations. If we have a projective point x colon y and y is not equal to 0, then we can rewrite that by dividing by y and getting the second coordinate equal to 1. And then that line is really represented by this number here, x over y. But that doesn't work if y is equal to 0. In that case, we're talking about this line, which is represented by 1 colon 0. So if we're interested in describing all the projective points here, and that's usually talked about in terms of this P1, which means the projective line, then there's really two kinds of ways of describing such things. There's points of the form x colon 1, where x is some rational number. And that's really exactly the same as an affine line, because this coordinate x is playing the same role as the affine coordinate along that line. But there's also one extra point. This point 1 colon 0 plays a different role from the other ones. It's like the point at infinity. And so it's often said that the projective line really is like an affine line plus one extra point. And this way we recover Desargues' original intuition that the projective line is the affine line plus one extra point. But now our understanding is more uniform. Our projective line is just the space of all one-dimensional subspaces here. And in some sense, there's really nothing special about this point here, except that we've decided to label all the lines by choosing, rather arbitrarily, this green line. If we had chosen some other green line, well, then our labeling would be different, but then this point wouldn't be special. Then there would be some other point that was special. So I really want you to think in terms of the projective line as being all these lines through the origin. That's what the projective line is. The space of all one-dimensional subspaces of this two-dimensional space, which is ultimately a one-dimensional object, which is essentially a line plus one extra point.